we have a particle moving along a curve with a position function, and they give us the derivatives of the components here, with respect to time. So these are the two derivatives. We know that the path of the particle is some function x of t and y of t. And they give us an initial position here, or a position at a particular time, time 4. They tell us the position is 1, 5. And in part A, we were supposed to find the acceleration vector of at time 4. So we know the acceleration vector of these essentially being the two velocity components. Acceleration vector is going to be the derivative of each of these at 4, if you will. And keeping in mind that with this being a calculator problem, we don't really have to find the derivative of radical 3t. I mean, it's not like they're terribly difficult to find the derivatives here, but ultimately, if we use our derivative at a point command, and we just find the derivative of that curve at that point, and we'll get our first component. So 0.433. If we do the same thing with our y coordinates, 3 cosine x squared over 2. Negative 11.872. And that would be our velocity vector. So again, time saving, recognizing that we don't have to find the derivatives here and plug in 4. And we can just use our derivative at a point, because that's all it is a derivative at a point problem. So that would be our acceleration vector. 1 point only for that one. On part B, it says find the y coordinate of the position of the particle at time 0. So we need to see what our displacement is. We know that our initial position in terms of y here is 5. Okay? So we're at 5 at the beginning time here. But the beginning time they told us is time 4, right? So we want to know what's the change in position from 4 to 0. And we know that that's going to be our y component of the velocity. So again, the area under that velocity curve is going to give us displacement, just like in y equals x equations. Same thing with parametric equations / vectors. Again, we're at 4. We're at 5 to begin with. That's our initial position in terms of y. Our displacement here, we want to know what's the position at 0, and we know that from the initial time they gave us was 4 here, so we're going from 4 to 0. That'll ultimately give us our displacement. And so if we do our integral command here, do our math 9 of 3 cosine x squared, so x squared over 2. We'll get our displacement as such, and again we're adding that to 5, and so final answer then is going to be that plus 5, so 1.601. So again, we're only focusing on the y direction in this case. Keep that in mind, we don't really have to do anything with the x's at all. We're looking just y direction only. And ultimately, again, that would be my position, the y coordinate, if you will, at time 0. 3 points here, one for having the correct integrand, one for recognizing that you need to integrate the dy dt, which is the y component of the velocity. Using 4, 5, in other words, recognizing that your initial position was 5 and not 0, if you will. And then ultimately the final answer was worth another point, so 3 total. Part C says on the interval 0 to 4, at what time does the speed of the particle first reach 3.5? So ultimately we need an expression for the speed of our particle here, and we know that in general speed is going to be the magnitude of the velocity, if you will. And when we have a velocity vector, remember if our v vector, if you will, is radical 3t 3 cosine t² over 2. We know that the speed of that when we have this, instead of a y equals x equation, it's just the absolute value of the velocity. It's still the absolute value of the velocity, but when we have components like this, then the absolute value of the velocity, remember, is the derivatives, components, if you will, squared. And then square root. So remember, that's how we calculate the absolute value of something that's in the parametric form. Right. And with that, we would get 3t in here, and here we get 3 cos, or 9 actually, 9 cosine squared of t squared over 2. Alright, and so again, this expression right here gives us the speed at any time. So this expression would give us the speed at any time, and the question is, when does this speed equal 3.5? So again, don't waste any time doing algebra. Just go ahead and calculate with your calculator, graph it, etc. So we got the square root of and we got 3t plus 9, and then we got cosine square root over 2 all squared. And then we want to know when that equals 3.5, and our time frame here is time greater than 0, so my window, I don't know if negative 10 to 10 will be an appropriate window, but we'll find out here. So we can see that there's our equation for speed, if you will. And our, I'm going to choke the window down a little bit here so we can see if there's an intersection point at that first one. Looks like that first one where it hits 3.5 would be right here. Use our intersection command. Get that cursor close to that point. And 3 times. 2.226. Be the result. Alright, so again, in review, our, when we have a velocity vector, if you will, or it comes from parametric equations, which are ultimately equivalent, we can write one from the other very easily. When we have a velocity vector, remember the speed is the absolute value of the velocity, which the absolute value is the square root of the 2 components squared, added together. And so we want to know when that speed is equal to 3.5. It's a graphing calculator problem. So an expression, if you had the expression for speed, which is this, it's a point. If you wrote the equation, if you essentially set that equal to 3.5, point, and you got the right answer with your calculator. One more point there. Okay, anything on part C? And part D, find the total distance traveled by the particle from time 0 to time 4. Well, again, we know that from time 0 to time 4, our total distance traveled is going to be the general formula here in this case is dx dt squared plus dy dt squared. You integrate that on 0 to 4, just like any other parametric situation we have. That's going to be our total distance equation. And from there, if we go ahead and calculate the integral of that. At this point, if I did my math 9, I would use my vars button and go my y vars function y1, because that's the equation that we have written in y1 right now. We already have that in there. And you have to retype that thing in there again. And comma x, comma 0, comma 4. And it should be 13.182. So 2 points for making sure you know the definition. 1 point for being able to put it in the calculator right. There's our 9. Questions? let's take a look at number 2 then. So we got there, looks like we have time greater than 0, and we have a rate function that represents speed in kilometers per hour at which a car travels along a straight road. Also have the number of liters of gasoline used by the car to travel X kilometers is modeled by this G function. And in part A, they ask us to find how many kilometers does the car travel in the first 2 hours. Well, remember, we were given this RFT function, which was in kilometers per hour, so if we find the area under that, that's going to give us kilometers. And it tells us that we want to know how many kilometers does it travel during the first two hours. If we write that, that's essentially the integral that we need. And it's a calculator problem, so we can not find it by hand. Now, one thing to consider there, though, remember, is if they want the how far does it travel, okay, we're actually asking for total distance here. So to be safe, what should we have around the R? Yeah, we should have absolute values around there. Now, depending on what the function's like, it could be positive valued, and we don't necessarily need them, but it can't hurt to have them. So we do our math 9 again. We do our absolute value, and the function is 120 times 1 minus e to the negative 10x squared. Alright, got 1, 2, send that one, 2 more, I guess. And we're going 0, 2. Should be 206.370 kilometers. And again, being a calculator problem, if you had looked at that function and saw that it was all positive valued, you don't necessarily need the absolute value part, but like I said, it doesn't hurt it to have it there, because ultimately we're looking for total distance. Alright, if you had the integral right, that was 1. Answer right, another one. Okay, let's see if we can handle part B. Part B says find the rate of change with respect to time of the number of liters of gasoline used by the car when the time is 2 hours, and we want to indicate our units of measurement. So if we want the rate of change with respect to time of the number of gallons used by the car, now keep in mind that our G function here is the number of gallons used by the, not gallons but liters, sorry. Apparently we're in Canada. Ultimately the number of liters used by this car is given by this G function. And ultimately, we want the change in that with respect to time. So we want dg dt. Okay? So right now we have a function g that's in terms of x. So if we just took the derivative of g, we'd get dg dx. True? Well, we don't really want dg dx. We want dg dt. It says. But remember, using our chain rule, if we wanted dg dt, okay, if we did dg dx, which we can certainly do because we have a function g in terms of x, okay, we could multiply that by dx dt, couldn't we? So that's true. Now, whether we can do anything with that or not remains to be seen. But bottom line is that would be a true sentence here using the chain rule. Okay. And so we can find dg dx. We can see that the derivative of that. And again, remember this is at a particular time here, so we don't really need to find the derivative of g necessarily. Okay, we want to find dg dt at 2. So if we find dg dx at 2, okay, we can just get the numerical answer for that using our calculator here. So the 0.05, and then it's 1 minus e to the negative x over 2. And we're doing it at time 2, right? So that turns out to be 0.00919696864. So that's our dg dx part. Okay. Oh, you know what? I lied. That's not correct. Scratch that. Ultimately here, this dg dx, remember our g is a function of x, which x is not a time, is it? X is not a time. X is a what? X is a distance, right? Okay. So ultimately, we can't find g prime, if you will, which is dg dx, and then stick a time into it because it's not, the x is not time. Okay? So we can't stick a 2 in there. Instead, what do we need to put in there instead? We need the distance at that time. Well, didn't we calculate that in our first problem? There's our distance, isn't it? Okay. So we need to put not a 2, but 206.370. Okay. So ultimately, that gives us 0, which is not right. Something's not right. I type in something wrong. No, it's a derivative. We want the derivative at that point, right? So we got g prime at time 2. At time 2, we're at distance this. Gotcha. There it is. Let's say something's fishy. There it is. All right. Insert our x. Now we'll try it. There we go. 0.05. That's what we're supposed to get. All right. So 0.05 is going to be our dg dx at that particular time. Okay. All right. And again, that's ultimately the first fraction here. Now, what about the second fraction, dx dt? Now, before we decide what is dx dt, think about what is x measured in again? X is measured in kilometers. And what's t measured in? Hours. So really, dx dt is measured in kilometers per hour. Okay. What do we have in this problem that's measured in kilometers per hour? What was our original function? It was r, wasn't it? And what's r measured in? Kilometers per hour. That is dx dt, isn't it? So I recognize that dx dt is r here for us. So we really just need r of 2. Because r is a function of time. Okay. So if I plug in r of 2, that turns out to be 120. So 120 times 0.05 ends up being 6. Alright, now let's figure out the units here. And it's easy to figure out the units if you consider the fractions as they are. G is measured in liters. X is measured in kilometers. And on the other fraction, x is measured in kilometers again. And time is measured in hours. So what are the units on our answer then? Liters per hour. So ultimately our car is using up 6 liters per hour total. Alright, 2 points for recognizing that you needed to use the chain rule here to figure out what dg dt is. Okay. This is not the only notation that we could have used here either. Ultimately, if we could, we have a g function that's in terms of x over here. If we just differentiated both sides with respect to t, okay, we'd ultimately get dg dx, the derivative as normal, times dx dt. If we differentiated g with respect to time, so there's a alternative way to do the actual work there, but this way it's just as easy as the other. But so chain rule part, getting the actual sentence was worth 2, and the answer with units worth another point. Okay, any questions on part B so far? Alright, then in part C, it says let t be the time at which the car's speed reaches, excuse me, read the question first. How many liters of gas have been used by the car when it reaches a speed of 80 kilometers per hour? So ultimately, we have an equation here that gives us liters of gas, okay? But ultimately, we need to know we need this gallons at a certain time, all right? So bottom line here is that we need to know when is this time when it reaches 80 kilometers per hour. Well, ultimately, IRT gives us kilometers per hour, true, and we want to know when that equals 80. Okay. So once again, this is a problem where we don't want to use algebra to figure out what that is. Okay. We use calculator. So if we put our equation in, get 120, and 1 minus e to the negative 10x squared. And we want to know when that equals 80. So window-wise, we need to go up to 100 here, let's say. time frame here, let me put it on 0, 2 here. Should I type that in right? -10x squared. Ah, there it is. That's why. So we gotta see something. There we go. Okay. So there's our R function and our 80. So if we do intersection command, .33 145,321. So that would be the time in question. Okay. So if you did that and got the right time, that was worth the point. Alright, now ultimately again we can't use our g of x function at this point because what does g of x require? It requires x. True? So x, remember, is a distance. So in order to use that g of x function, which is 0.05x and then 1 minus e to the negative x over 2, okay? In order to use this, we need to know an x here, and ultimately we need to know the number of kilometers at that time. Well, the number of kilometers at that time, remember, is going to be found just like we did in part A. Okay? We'd have to do the RT integral from 0 to 0.33145321. And wouldn't that give us an x value? That would give us our distance traveled. We've already seen the function. We know it's positive value, so we don't need to do absolute value. I mean, like I said, we can if we want to, but we don't necessarily need to in this case. All right. So if we integrate and we do our RT function, which we already have the RT in our y1, remember? Okay. So we can do our bars function y1. And we're going 0 to 0.33145321. And we get that as our x value, so that's our x at that particular time. And remember, all we're doing with that is we're plugging it into our g function that we have here. So if we type in 0.05 times our answer, and we multiply that by 1 minus e to the negative answer divided by 2. You get 0.537. Remember, that's in liters of gas. Alright, obviously not the hardest problem in the world to deal with, but ultimately you just got to make sure you're careful with what the functions are in terms of, and make sure that we use the right numbers. Like I said, be careful not to put a time in where it belongs a distance, etc., or vice versa. Okay. From that, you're good to go. Other points here, if you calculated the distance, that was worth 2 points. If you set up that integral to find the distance at time 0.331 or whatever. And then finally, final point was for the right amount of gas. Questions on part C? Okay, next one then. Number 3 gives us a variety of information here. Basically, it says gives us the distance from the river's edge, and then it gives the depth of the water. Essentially, we're going across the river. It's giving us different measurements for depth of the water. And it says the scientists measure this depth. The river is 24 feet wide in this location. The measurements are taken in a straight line perpendicular to the edge of the river. The distances are shown in the table above. And it says the velocity of the water at this point, feet per minute, is modeled by the v function given. And the time frame we're working with here is 0 to 120, so we're working with the first 120 minutes of this experiment. And part A says use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the area of a cross section of the river at Picnic Point in square feet and show your computation. So bottom line here is we have a trapezoidal sum to deal with. We have the data in the table, and our first trapezoid is going to be 1/2 times the height, remember, is going to be the x distance, which goes from 0 to 8, and then the 2 bases are going to be the depths, which are 0 and 7. And the second one, it goes from 8 to 14, so that would be 6, and the 2 heights are 7 and 8. And the next one goes from 14 to 22, that would be another 8, and the heights are 8 and 2. And then the last one, we're going from 22 to 24, that's 2, and then our heights are 2 and 0. And ultimately we're going to add that all up and we're going to get our result. So let's find out what that's going to be. So in the first one, we get 4 times 7, that's 28. Second one, we got 3 times 15, that's 45. This one we have 4 times 10, that's 40. And this one we have 2 times 1, that's 2. And so ultimately we get, these two make 73. 73 and 40 make 113. 113 and 2 makes 115. Okay. We know the units are feet squared here because it told us so. Okay. But let's think about why else the units here would be square feet. Why are we getting square feet when we do this? Remember, if we were to draw a picture of that function, okay, we have our x values here, the distance from the river's edge, which is measured in feet, and we have the y values, which is water depth, which is measured in feet. So if we were to draw a picture of this function, and then hence calculate the area under the curve, where our area is always going to be the x units times the y units. So what are we going to get? Feet squared. Okay. So that's another reason why the answer here for this cross-sectional area that we're finding here is in feet squared. Okay. Alright, man, only 1 point, darn it, for all that. Okay. Alright, now, part B here says that the volumetric flow at a location along the river is the product of the cross-sectional area, which, keep in mind, that's what we just found. Okay. So it's the cross-sectional area and the velocity of the water at that location. So let's think about that. Our new function that they're giving us, that they didn't actually write for us, but they're telling us what it is. This volumetric flow function is the cross-sectional area. So at this picnic point, if you will, it's 115 is the cross-sectional area. And the velocity function, that was given to us in the reading. True? So that right there is our, this is the volumetric flow is the product of the cross-sectional area and the velocity at that location. So this is our volumetric flow function, I'll just call it F. Okay? And it says use the approximation in part A to estimate the average value of the volumetric flow at Picnic Point. So again, we've written our volumetric flow formula. We know the average value of that is going to be the integral from A to B of our function on a particular interval. And our time frame here is 0 to 120. And so if I want the average value, I'm just going to set up my average value integral as such. And that would do it. And from there, it's a calculator problem because it's on the calculator part. So if we do our math 9, and we do our 115 times, and our volume function is 16 plus 12 but 2 sine, and then it's square root of x plus 10. Let's see, finish all my parentheses, got one more. X comma 0 comma 120. Alright, and that right there would give us the integral part, and then of course we're dividing that by 120 to get the average value. Get 1807.170. And the units on this, remember this is a volumetric flow function. This is measured in feet squared. The volume function is measured in feet per minute. So if we do feet per minute, feet squared times feet per minute, that would be feet cubed per minute. And remember the integral would not make it feet cubed per minute, but we're dividing it again by minutes here. That's how the integral itself would just give us the feet cubed. The volume here would give us, or divided by 120, which is in minutes, would give us the feet cubed back to feet cubed per minute. So remember, whatever the function is measured in, the average value is also measured in that same unit. Alright, 3 points if we got the 0 to 120 and the 120 part. Got a point for having that. Got a point for having the correct integrand, and we got a point for having the correct answer. Okay, questions so far? Alright, and then part C says, suppose a scientist proposes that the function f is, which is 8 sine of x, pi x, that is, over 24. So pi x over 24, that's our function. It says that is the model for the depth of water in feet at Picnic Point. So instead of giving us a set of points here, they've given us the function as an equation instead. And bottom line is we want to find the cross-sectional area of the river at the Picnic Point based on this model. Well, keep in mind up here, when we were given the data instead of the equation, we still just found the area under the curve. We had to use a trapezoidal approximation to find the area under the curve. Okay? But that's going to be no different than what we do here. We're still just going to find the area under the curve, so we're going to go 0 to 24 of our f of x function, and that's going to give us our cross-sectional area. And remember why, again, this f is measured in feet, okay? And it's feet versus feet, so therefore what's the area under this curve going to be? Feet squared. Still gives us the same result, whether we find the area of the cross-section using a data situation with the trapezoidal rule, or we find it using an integral because we have an actual function. And ultimately, if we type that into our calculator, just for time's sake, we're going to get 122.231 feet squared, so that being our cross-sectional area. And we get 2 points for that, one for recognizing that we needed to write an integral for the f function, one for getting the right answer, 122.231. Alright, and finally, the part D says recall that the volumetric flow, and this says recall because you had to remember from a long time ago that you heard that, right? One problem ago. So the volumetric flow is still the cross-sectional area and the velocity, product of those two. And it says to prevent flooding, the water must be diverted if the average value of the volumetric flow at Picnic Point exceeds 2,100 cubic feet per minute for a 20-minute period. So using your answer from part C, find the average value of the volumetric flow during the time interval 40 to 60, and does this value indicate that the water must be diverted? Okay. So ultimately we're going to set up the same thing that we just did right here. Okay. But for this particular case, at Picnic Point, remember this is our cross-sectional area. Remember above it was 115 because we did it with the trapezoidal approximation. So our estimate from that was 115. Okay, our estimate from this was 122.231. Okay, so ultimately we're still going to set up the same kind of equation here. We're going to go from our 122.231 times v of t. Okay, and remember our v of t function is given still, same v of t function we used above. And so we're going to do that on that 20-minute period from 40 to 60, and we're going to have our absolute, or not absolute value, but our average value. We're going to have 1 over 20 out in front, because that's the time frame. So again, they're asking us that on this particular time frame from 40 to 60, what is that volumetric flow? And just before we find the answer, remember the volumetric flow before was 1807. So at that point, okay, we could say, yeah, the water doesn't need to be diverted. It's not over 2100. True? Okay, but remember, this is over the whole time from 0 to 120. So maybe in this 40 to 60 time period, maybe it goes over 2100. Okay, it might, but we'll find out. So if we type that in, and again, it's just a matter of, you can type that in on your own, just time's sake, we get 2181.913 cubic feet per minute. So what could be said about that time 40 to 60, that the volumetric flow is too big or good to go? So the river needs to be diverted if it's over 2100, so this is what? It's too big. So we would say yes, divert the river. Okay. Alright, so a point breakdown there, 3 points, one for writing the integral again, which ultimately we did that. Same thing in part B. If you found the volumetric flow, the average value of that, you get 1 point for that. And then your answer with a reason. Ultimately, if you recognize that that was the right answer, that it was over 2100, you said yes, divert the river because it's over 2100, then you get that final point. Questions?